Welcome to the Distributed Energy Experience, brought to you by Power Magazine. Thank you for joining us today, and we hope you will make the most of this week's event by getting more involved. There are many ways to participate throughout this platform and within each session. So before we get started, allow me to mention a few items you may have missed. First, be sure to register for all sessions you want to see during the week. By registering, your attendance will be recorded and you will be given Professional Development Hour credits at the end of the week. Take time between sessions to visit with others. Just like you would if you were live and in person, look at others attending this session and strike up a conversation. Or take a moment to visit the booths and connect with the event supporters. Review all of the opportunities the platform has to offer, like the discussion forums. We have set up several discussions where like-minded conversations can take place to continue outside of the sessions. Please participate. Don't be shy about asking questions, making comments, and check out the polling questions that are available in each session. There's one available right now for you to answer. Participation is the best way to get the most out of your time. Finally, tell us how we're doing. After every session, there will be a survey opportunity, so click on it and rate the sessions and the speakers. By participating, you can possibly win prizes. So register for sessions, connect with others, join the conversation, ask questions, answer polls, complete the session surveys.
Now, let me introduce our moderator for today's session, our final session of the day. We're glad to have our editor of Power Magazine, Daryl Proctor, leading this discussion. So take it away, Daryl.
Thanks for that, Kim, and good day, everyone, wherever you are around the globe. I know it's still morning on the U.S. West Coast, afternoon or evening in Europe and Asia, and we're happy to have all of you here with us today for another session of Power's Distributed Energy Experience. Our speakers for this session will focus on virtual power plants and the VPP's role in grid management. Virtual power plant is a network of decentralized power generating units as well as flexible power consumers and storage systems. Virtual power plant model of DER aggregation and optimization is spreading across the world to respond to the need for increased grid reliability and to lower the cost of renewable energy integration. In this session, we'll hear from Alexandra Radwanska, International Business Development Manager for NextKafka. Alexandra is responsible for the international sales of NextKafka's VPP as a service solution. She also supports partners in realizing their VPP and business models. We'll also get insight from John Grooters, Business Development Director, Grid Innovation for Minsait ACS. John is a power system engineer with more than a decade of experience in both utility and industrial applications. He's passionate about distribution, modernization, and bringing solutions to a dynamically changing utility power grid. The session also includes Brent Nelson, Manager of Resource Planning Consulting for Ascend Analytics. Brent is an energy expert with research experience in academia, government, national labs, and consulting, spanning topics in energy efficiency, renewable energy, and energy economics and policy. He is co-presenting today with Amy Bailey, who is Director of Decarbonization and Grid Innovation at Silicon Valley Green Energy. Amy's work centers around identifying and managing technical, economic, and regulatory barriers and opportunities to achieve decarbonization. Finally, we'll hear from Rahul Kar, General Manager, New Energy for AutoGrid Systems. Rahul is responsible for revenue growth, product development, solutions design, and delivery of the new energy business unit at AutoGrid. Welcome to all our speakers and to our worldwide audience. And with that, I'll turn it over to Alexandra.
Hello, everyone. My name is Alexandra Radwanska. As introduced, I work at the company called NextKafka. We are the European company. And I'm very happy to speak today on this panel with such amazing co-speakers and also share insights from our European case study, which involved a power-to-gas facility that was supposed to produce green hydrogen because before it was coal worldwide. So Let me very briefly introduce NextKafka to you, because I assume that many of you do not know us as well. We are a global VPP platform provider. So we enable aggregators, utilities, traders, independent power producers to build their own virtual power plant. We base this service on our own experience in running a VPP. Because here in Europe, we operate a mixed asset VPP, currently aggregating over 9 gigawatt of installed capacity. That consists of almost 10,000 energy generators, energy consumers, and storage units. We work on the technology of a virtual power plant. I think that at this point of the conference, everyone knows what a VPP is, but let me briefly sum it up for you. So VPP is a cluster of networked decentralized energy resources. It allows to aggregate thousands of electricity producers, consumers, storage units, and to control them according to the needs of their operator. And a virtual power plant can effectively network, forecast, optimize, and dispatch fleet of coordinated DER, such as wind, solar, bioenergy, hydropower, batteries, electrolyzers, and many more. This technology enables managers of portfolio of distributed renewables, for instance, to, for example, react to signals coming from the system operators, or to adapt the generation of, say, renewables to certain price signals. So also on top of that, DER, thanks to a virtual power plant, can deliver certain system services. But as a business developer, I think that apart from discussing technical functionalities, it is also important to figure out how to monetize the flexibility of DER that is unlocked with the virtual power plant. And in fact, to ask a question, what is the business case of a VPP operator, or to use a synonym, an aggregator? As a matter of fact, energy markets in the US and in Europe are quite different. I think everyone knows that. In my opinion, it is important to remember that while in the US, demand response has historically served as the basis for the VPP concept or definition, in Europe, we rather speak about the large-scale supply-side VPP. Additionally, all countries in the EU at least have deregulated electricity markets. Many have done it already 20, 30 years ago. So now in the deregulated wholesale and the ancillary service markets, the non-utility providers can not only simply sell their electricity or to buy electricity from thousands of providers, we can also actively deliver needed capacity and energy to help transmission system operators balance the grid. For example, in Germany, it is already allowed to deliver frequency stabilizing services since 2011. And in fact, NextKafka was a pioneer in this field. Once we already understand the context, let me move to the case study. Due to the time limitation, of course, and the complexity of the project, I'll only present the helicopter view of this case study. However, if you'd like to know more, please approach me on the event platform or via email. So coming to the point, this power-to-gas project was realized by NextKafka in cooperation with Greenpeace Energy and Stadtwerk Haßfurt, with the aim to evaluate the possibility to locally use the excess renewable generation and to reduce exports of this electricity from the distribution system to the transmission system. We wanted to use the surplus of available renewable electricity to generate green hydrogen through electrolyzers. This electrolyzer belongs to the public utility Stadtwerke Haßfurt, but the control of the whole power-to-gas plant is in fact split between the controls on site and the control center of NextKafka's virtual power plant in Cologne, which is roughly 360 kilometers away from this location. So to put you into the context, Haßfurt is a small town in the middle of Mainfranken, which is a Bavarian region in southern Germany. The electricity consumption of this city is between 4 and a maximum of 13 megawatt. The electricity consumption is offset by a supply-dependent renewables-based generation of almost 50 megawatt. According to Stadtwerke Hasport, this leads to large local surpluses, of course, in the distribution network. And so far, the surpluses of electricity have been fed into the upstream transmission grid. To avoid this costly export of the electricity, as well as to increase region self-sufficiency, Stadtwerke Hasport decided to use this green surplus of electricity to power an electrolyzer and to produce synthetic hydrogen. By activating the power-to-gas plant, the local consumption increased, of course, thus reducing the outflow of the electricity to the transmission grid. The power-to-gas plant in Hasport consists of the electrolyzers unit with a maximum power capacity of 1.25 megawatt, a gas storage facility with a volumetric capacity of more or less 1,700 cubic meters, and 2 connections to local piping system, which is for the natural gas network in the city, and another connection, which is a direct connection to a malting plant. I think it's called Malt House, or it's a part of a brewery in the city. The P2G system is connected to the medium voltage level of the distribution network, and the installed capacity corresponds to about 10% of the peak load of the total electricity consumption of the city of Hasport. In this project, we use a PEM electrolyzer of a very popular German provider. This type of electrolyzer was particularly suitable for this project because it could be controlled nimbly and without any bigger restrictions. So in fact, any operating point was reached within 20 seconds. That means that the power-to-gas plant could be ramped up at the full capacity within 20 seconds. And at this full capacity, it was capable of producing 225 cubic meters of hydrogen per hour. And in fact, taking into account that the calorific value of hydrogen is about 3.5 kilowatt hours per cubic meter, we achieved the conversion efficiency from electric energy to chemical energy of more or less 70%. The power-to-gas plant was, of course, operating according to the local electricity demand and the availability of the renewable energy in the local grid. So looking at the actual business case, we can say that the electrolyzer had 2 revenue streams, or was delivering 2 activities which both generated separate revenue streams. First revenue stream was, or first activity was using excess renewable energy to produce hydrogen. Of course, this hydrogen was solved, which is one revenue stream. And the second activity is providing grid frequency to grid frequency control. We call it balancing service to the transmission system operator. And in fact, this electrolyzer was capable of delivering 3 main products of the balancing service market that we use in Germany. These are frequency containment reserve, automatic frequency restoration reserve, and the manual frequency restoration reserve. Now that I told you everything about the operation principle of the electrolyzer, let's have a look at what actually happened with the product of the electrolyzers. So the hydrogen was either stored in the storage tank for some time, or it was delivered directly to the local malt house, to the brewery, or it was injected into the natural gas network of the municipality. The gas network and the malting plant were supplied separately due to different hydrogen tolerances in the pipes. So that was 10% for the malt house, but unfortunately only 5% for the public gas network. I have to mention at this point that Greenpeace Energy, who is an electricity and gas retailer, offered their climate-conscious customers special tariff, which was called wind gas. That was offered together with a standard contract for sale of natural gas. And in fact, these clients had an opportunity to cross-finance the project via special tariff. And they were, of course, burning a mixture of natural gas and the green hydrogen in their gas heaters without any upgrades in their homes. On this graph, you can see the actual time series, a real time series screenshot took from our control center. So what you can see on the graph, in blue, you can see the generation of the wind portfolio. In dark yellow, you can see the PV generation that, of the PV portfolio that was around the city, but also there is the residential rooftops. It's included together. In dark orange color, you can see the electricity consumption of the municipality, including the industrial customers as well. And below here in this graph, you can see that the electrolyzer actually turns on or ramps up when the surplus of the electricity, of the green electricity, occurs in the local distribution network. So the whole orchestration of this project was in hands of NextKafka. And what did we practically do? So first of all, every 15 minutes, NextKafka delivered a forecast on the generation of PV and wind portfolios, gas and electricity consumption in Hasford, so in this municipality, and the gas consumption of the nearby melting plant, so this brewery that I mentioned before. The virtual power plant converted this data directly into the control signals that were sent to the electrolyzer. So depending on the price forecast and the current utilization of the gas and electricity network, the VPP remotely started or stopped the electrolyzer, or ramped up or ramped down if there was such a need, the electrolyzer. While of course at the same time standing by to deliver at any moment of the time the balancing service to the transmission system operator. So additionally, in fact, NextKafka facilitated a CPPA between the renewable portfolio and the electrolyzer or power to gas plant. So instead of selling electricity to the market for a negative price, the electricity was sold to Stadtwerke Hasford at a very competitive price to power the electrolyzers. To realize this project, we mobilized all underlying technical capabilities of the VPP. So we were monitoring the portfolio in real time and the electrolyzer in real time. We forecasted the renewable generation, and we were updating the forecast every 15 minutes. We controlled the electrolyzer, we steered the electrolyzer, which we can treat as a kind of demand response unit. And we were also delivering the ancillary services. Summing up, I must say that although this P2G plant in Hasford was a pilot project, we started in 2016, which is 4 years ago, sorry. As one of the, and it was one of the first projects of this kind, we see now that it, in fact, can compete on the market under current economic conditions. And apart from that, all cooperating parties leverage their capabilities so that the practical integration of the electrolyzer to the VPP was successful in terms of both control technology and the operation. With that, I thank you for your attention, and I'm really looking forward to your intriguing questions in the question round at the end, right?
That's correct. Thank you, Alexandra. And I definitely will be coming back to ask you about hydrogen, which is really making inroads into the power industry at the moment. Again, thanks to Alexandra for that presentation. And next we're going to hear from John Grooters of Minsait ACS. Take it away, John.
All right, thank you. Good evening and good afternoon to everybody, and I guess good morning to the West Coast. So pleasure to be on this panel and look forward to some of the questions that are going to come up. So just a quick background, I work for a company called Minsait ACS. We're a global software technology provider. We get into both operational technology as well as informational technology, and certainly encompassed in that is a lot of capabilities within the virtual power plant space. So what I was going to focus on in my short introduction is really the coordination trends that we're starting to see with virtual power plants. Traditionally, when virtual power plants started coming about, they were pretty well siloed. Obviously, some coordination with the market that they're bidding into, but other than that, there weren't a lot of other stakeholders that had to be coordinated. So what I wanted to talk about and focus on today are three specific stakeholders that are going to see an increased coordination trend with virtual power plant providers. So those being, and I should clarify, I'm presenting this through the lens of a North American outlook, certainly as we had heard the markets and just the way the utility grids operate are certainly different in Europe and elsewhere. So this is mainly through the trends that we're seeing in North America. But really the three stakeholders that we're going to talk about is the distribution operators or the distribution utilities, how they will have more interaction with virtual power plants, as well as transmission operators, especially when we're talking about resiliency and reliability. And then also markets, certainly that's always been there, but there's going to be a lot of reasons for that, for increased coordination in those markets that we'll touch on. So with that, the first one, coordination with distribution operators. Traditionally, there's been very little coordination between a virtual power plant and the end distribution network that the DER is located at, other than certainly that DER asset has to work within the jurisdiction and abide by the interconnection requirements. But other than that, there's been very little interaction, and distribution utilities are certainly trying to get a little bit more out of the DERs on their grid. So one of them use case that we're constantly seeing more of is leveraging that aggregation of DER in a more targeted grid service approach. So instead of it being a system-wide event, they're looking at maybe more targeted into certain substations or feeders to assist with that distribution network. That coordination is definitely going to increase as more of these utilities require virtual power plants or DERM systems to be integrated into their SCADA and ADMS platforms. We're definitely seeing that trend. Another use case is distribution operators want to use the DERs in more of a dynamic operation. So traditionally, demand response was scheduled hours or days ahead of an event, where distribution utilities are looking to make that much more dynamic to be able to adapt to forecasting and system events much quicker. This certainly means that they'll have to adjust their programs, rates, et cetera, and it will lead to more of an automated response and dispatch. The other trend we're seeing with distribution operators is being more cognizant of customer fatigue. So their utilities are being much more conscious of their customer needs, and they don't want to negatively impact either their comfort or cause fatigue by calling on their assets too often. So this is another coordination requirement that definitely is out there. And then the final one for distribution is value stacking DER assets between both a bulk electric system support as well as a distribution support. So again, distribution utilities want to maximize these assets. A good example of this would be a distribution utility that procures a large battery storage, and certainly maybe the primary use case is to reduce peak demands, but also they may want to use it during a loss of distributed generation, say cloud cover, and loss of a lot of rooftop solar, and therefore a sharp increase in load. They'd also want to be able to use that battery storage in that use case as well. So certainly that would require more coordination, especially because you potentially could have competing objectives for the same DER asset. So that is some of the additional or the requirements or trends we're seeing as far as more coordination with distribution operators. So let's move on to the transmission system and coordination with the transmission operators. So in areas that are maybe not part of a vertically integrated IOU, oftentimes there is a generator and transmission provider or a G&T And we are definitely seeing the G&Ts increasing coordination with their member utilities to increase visualization and potentially leverage that aggregation of DERs on those various member distribution systems. A big trend of that is also due to the fact that these G&Ts are retiring a lot of thermal plants with renewable generation. Therefore, they are going from a more dispatchable to a less dispatchable and more intermittent generation mix, which therefore really does require them to look at ways of trying to control load flexibility, and coordinating that with their member utilities is one way of doing it. A prime example of this is happening in my home state in Colorado, where Platte River Power Authority, which is the G&T in northern Colorado, and they serve 4 different northern Colorado municipalities. They've actually formed a DER committee with themselves, as well as all the stakeholders within the other municipalities, to try to come up with a cohesive DER strategy. How can they all work together, be transparent, and essentially just increase that coordination? So certainly a trend that's happening here, and I know it's happening many other places. Also, balancing authorities are increasingly wanting better forecasting from the increased DER penetration. And obviously at the transmission level, making sure that reliability is there. As DER aggregation grows, they will have a direct impact on that reliability at the transmission level. A perfect example of this is I was fortunate to be a member on the IEEE 2030.11 DERMS working group, and one of the key participants in that working group was NERC. So certainly, those having that that coordination with the balancing authorities is going to be key. And then finally, locational awareness of the DERs, to associate the DERs and the aggregation of DERs with transmission nodes. This is already in effect at New York ISO. They already have a requirement that you can only aggregate DERs that are associated with the same transmission node. So that locational awareness is another driver for increased coordination. So finally, coordination with markets. Again, virtual power plants have certainly been coordinating with markets since their inception, but there's a few things happening that are going to be a catalyst for increased market participation and that coordination with markets. So 2 of them, which I'm sure most of the audience is well aware of, FERC 841, which was passed earlier this year, and that basically led the way. What it did is it told the ISOs and the RTOs that they have to remove the barriers for energy storage to participate in the wholesale markets. But then just recently, FERC 2222 was also passed, and that really extended that same order to all of DERs in aggregation. So this meant all the DERs can be aggregated, no matter the type they are, and basically is going to remove a lot of the barriers that are currently in place. So even though a lot of DERs were participating in markets, it was mostly at a demand response level. This should open up the capabilities for them to bid into capacity, energy, and ancillary services in those various markets. Again, we'll see how this all plays out. It's basically just an order telling all these entities to remove the barriers. But some of the key parts of FERC 2222 are basically outlining that all of these entities have to address technical considerations, and some of them are coincide with what we've talked about today. So locational requirements for the DER aggregators, we just talked about that. Distribution factors for bidding parameters. So again, making sure that the constraints of the distribution grid that all the DERs are located at are taken into account. Also, they have to account for the information and data requirements. All this increased coordination, increased participation will greatly increase the amount of data that is required that all of these entities are going to have to take into consideration. Also, along with that, metering and telemetry requirements that are going to need to be required. And then finally, one of the key takeaways of FERC 2222, and probably the reason why I chose to talk about coordination as the key concept, is they really address the fact that coordination among the regional grid operator, the DER aggregator, the distributed utility, and relevant retail regulatory authorities, all of those need to be clearly addressed by all these entities. So certainly is going to lead the way for more DER participation, and look forward to answering some questions as they come up.
Okay, thanks for that, John. A lot of information there. We're going to come back to that in our Q&A session. Next up, we're going to hear from Brent Nelson of Ascend Analytics and Amy Bailey of Silicon Valley Clean Energy. Take it away, Brent and Amy.
All right, thanks, Dale. So we are going to talk to you about a project that we at Ascend did for Silicon Valley Clean Energy. I'll let Amy tell a little bit more about that in a second. A little bit about Ascend. We are about 20-year-old consulting and utility support company. We have software that does production cost modeling. We support a variety of utilities and community choice aggregators, retailers, project developers in doing valuation of energy resources. So we work kind of across the spectrum with a lot of different folks. And Amy can talk about Silicon Valley.
Sorry, I think I have to unmute. Thanks. Thanks, Brett. Great to be here. By way of background, Silicon Valley Clean Energy, or SVCE for short, is a community energy agency, or so-called CCA, serving 13 communities in the Bay Area. The communities listed here on this slide on the right. We were formed by these communities in 2016 to take bold action on climate change. Next slide, please. And we have a decarbonization strategy where we've adopted this overarching approach. First, we procure and maintain a sustainable, affordable, and carbon-free power supply. We are an electricity provider, so this is really our bread and butter. As of last July, we've made over $1 billion in investments in renewable energy projects, and we're working to try to accelerate the transition to a decarbonized grid by driving innovation. So for instance, we have an RFO out now for long duration storage. The second part of our approach is to electrify everything, specifically buildings and transportation, such that these sectors are powered by renewable energy. And those are the largest sources of greenhouse gas emissions in our service territory at this point in time. So most of our customer programs, for instance, focus on helping our customers move away from fossil fuels to advanced electric technologies. Then the third part of our approach, where we tie this together by focusing on energy efficiency and grid integration, the latter of which is of course the focus of this talk. And so SVCE, we carried out, next slide please. We carried out two primary activities in 2019 focused on grid integration and VPPs in specific. We published a white paper with Gridworks exploring various pathways for community energy agencies such as ourselves to proactively support grid integration. And a link to that white paper is included on the slide here. Then following that white paper, we carried out this valuation assessment to help really further guide our grid integration activities. So I'll turn it over to Brent to cover the details of that stuff.
Thanks, Amy. So at a big picture, virtual power plant, as I'm sure folks know, really an aggregation of various resources. Load flexibility, energy efficiency, behind the meter generation, behind the meter storage. And what we wanted to do with this project is to take a step back and say, okay, there's all these different resources. If we're going to try to design a program strategically, which resources are going to provide the greatest value? How would we realize those values kind of from an operational standpoint? So what's sort of the best mechanisms in order to get value out of these resources? And if we're going to design a program, how should we strategize and how should we prioritize which resources we focus on and how we structure incentives and things like that? That's where we came in to work with Silicon Valley Clean Energy to actually do the valuation work. So valuation is a core part of what we do. We do a lot of valuation work with storage resources, with thermal resources, working with utilities on kind of forecasting long-term market trends and understanding how to maximize value of the resources that they have and the assets that they have. So to kind of help frame the analysis, sorry, a couple of pieces of terminology will be helpful. We looked at two different market mechanisms, which are really mechanisms that determine how you actually realize value. One is load shaping. So this is where we would use these VPP resources internally to alter Silicon Valley's net load. So think about it as like, you know, behind the meter for the utility itself. So as they interact with the larger California markets, one mechanism would be to use and deploy these resources in a way that affects the load that reaches the market interactions. The other way that these resources could generate revenues is through a market integrated approach, which is where these resources would sell to the market. So in one case, we're altering the load that needs to interact with the market. In the other case, we're using these resources on the supply side to sell into the market. We also looked at 4 different value streams that different resources could generate value from. The first was a capacity value in California that's called resource adequacy, or RA. So what's the capacity value of the resource? And so that's either a payment that it would receive or it's an avoided expense by altering the net load. We looked at day-ahead energy arbitrage, so basic arbitrage between high and low prices, moving load from high-priced hours to low-priced hours. Real-time energy arbitrage, same thing, but for the real-time energy market. By the way, real-time energy markets are an often underappreciated part of resource valuation, particularly for flexible resources that can respond in very short time periods. There's a lot more volatility and a lot more up-down movement in prices in the real-time market, and so a lot more value can typically be generated there. So that's an important part of valuation. We also looked at the value that could be generated in ancillary services, so providing spin or providing spin or regulation. And one note on ancillary services is that would only apply to the market integrated lens. So if we're just doing load shaping, kind of changing the demand for Silicon Valley, ancillary services isn't something you can do through that approach. So the way that we went about estimating the value of these different resources followed the steps on this slide. First step was we tried to estimate the value per kilowatt that a given resource could provide for a given revenue stream. So if you had, for example, electric vehicle load flexibility, what would be the value for being able to flex 1 kilowatt of electric load? And what would that value be in the real time? What would that value be in the day ahead? What would that value be for capacity? Could it play in ancillaries? If it can, what would the value be there? So we used 2018 data as a reference year. So that was kind of our starting point because we had a full set of 2018 price data for all of these different revenue streams. So we started there, and then we defined an expected hourly availability. So the idea is that electric vehicle charging flexibility isn't helpful unless the electric vehicle is plugged in. Energy efficiency for an air conditioning system isn't helpful unless the air conditioning system is operating. So we had to sort of break down an expected hourly availability to determine when a resource could provide value and when it couldn't based on when it's operating and available. So then we determined the value that each asset could provide for each value stream in this 2018 reference data. We then took our long-term forecasts for how ancillary prices are going to evolve, for how real-time prices are going to evolve, day-ahead prices, et cetera, in order to estimate the future dollars per kilowatt value. So how is now going to change as we look out into the future? And then step 3 was to estimate the total available kilowatts. So how much electric vehicle load flexibility is possible, how much air conditioning efficiency is possible, how much behind the meter storage is possible. Then if we have total kilowatts and we have dollars per kilowatts, we can get an annual total value. And then we took an NPV for the period for 2020 to 2030. So some of the key takeaways from the analysis, the first one is that load shaping, so kind of the demand side approach, enables the highest capacity value and is significantly easier to manage than a market integrated value, the supply side approach. The reason for that is that in order to be an eligible capacity resource in California, there's a variety of rules and requirements to be eligible. Whereas if you're working on the demand side, anything you do to reduce your coincident peak load becomes valuable. So it's easier to generate that value. We see the highest value streams coming from capacity value and real-time energy arbitrage. The most valuable asset by far, and I'll show this in a second, is EV charging. So being able to flex EV charging from non-productive times to more productive times carries a lot of value. But one interesting note is that if people follow time of use charging rates, a lot of that value gets realized just through people following time of use rates. So there's a lot of value in trying to get people to follow time of use electric vehicle charging, particularly if you forecast a lot of EV growth. So to put that into graphical form, what this graph shows is that 10-year NPV on the y-axis, 4 different revenue streams going across the x. So RA is capacity, day ahead is energy arbitrage in the day ahead market, RT is energy arbitrage in the real-time market, and then ancillary services is only applicable to the market integrated lens. And for each of these revenue streams, we have a bar for LS is load shaping, so that's the demand side approach. MKT is market, so that's the supply side approach. And a couple key takeaways here. We get a lot more value, as I mentioned, for the demand side approach, and that's because there's just less restrictions about what's eligible and what qualifies. Whether you're looking at load shaping or market integrated, energy arbitrage is about the same. The reason that that's important is that a lot of nodes are more volatile than market hubs. But the problem is that when you aggregate over several different nodes, a lot of that volatility disappears. So whether you're looking at load shaping, which you can do at a smaller aggregation than market integrated, which is typically at a larger aggregation, it doesn't make that much of it, or sorry, the other way around. Load shaping is a larger aggregation, market integrated is smaller. But it doesn't make that much difference because you have to aggregate over enough points that it doesn't provide much benefit one way or the other. So the next question that we were interested in is really which resources. So if you're going to design a VPP strategy, what are the resources that really matter? And in the case of Silicon Valley, Bay Area, a lot of interest around electric vehicles. There's a lot of anticipated EV adoption. This gray bar is the value that's just due to electric vehicle load flexibility, if you can flex that load. And so what that means is that what really matters is electric vehicle load. So that sort of dominates above everything else. The reason for that is that as we look at electric vehicle adoption, a lot of the charging is likely to happen right at the most inconvenient time for the grid. So back in the day when people still drove to work, if people come home and then plug in their cars, that means that you're going to have a huge surge in load right as the sun is going down and you're having a huge drop in supply. And that's already the most volatile price period. And that's also when capacity really matters. So having a huge surge in load right in the key capacity hours is really problematic. And so being able to flex that out of that window, maybe to overnight periods, generates a ton of value. Potentially also shifting the other direction during peak solar generation has value as well. But either way, flexing it out of the 5 to 9 p.m. window post work, early evening, generates a ton of value. And we see in these stacks that that's the big driver of value. We did the same thing, assuming that EV charging follows time of use rates. And what you see is that those gray stacks disappear almost entirely. So before, huge part of the bars, afterward, much smaller part of the bars. That doesn't mean that EV charging isn't important or that time of use rates aren't good. What it means is that if you can get people to follow time of use rates, you'll already supply a lot of the value that being able to have active control about flexing load provides. So the goal is to move EV load out of inconvenient times. If you can get people to do it on their own, great. If you can if you can do it through some sort of active control approach, also great. Either way, the key is to get it out of those hours. We also see a little bit of value for smart thermostats. Those being able to move load around a little bit. There's some flexibility there. The house basically functions as a thermal battery because it has some resistance to temperature movements. So that creates a little bit of flexibility, and that has value as well. So The analysis that we did was a little bit simplified. There are things that get a little more complicated. First of all, we were looking at each revenue stream in isolation, but revenue streams can actually also stack. So capacity value and day ahead energy arbitrage stack well, because typically the peak capacity hours are also the hours that are the highest cost in the day ahead market. Stacking capacity value and real-time energy value is a little bit less clear. The reason for that is that real-time price spikes are shorter and short in duration and typically very volatile. And so the deployment of an asset that's going to provide the most value for real-time energy may or may not align with peak capacity hours. Day ahead, our energy arbitrage and real-time energy arbitrage can stack somewhat. So there is some real-time volatility that shows up during low-priced day ahead energy hours. And so being able to flex around in that area can provide some value. Also, under California rules, you can stack spin ancillary value on top of real-time energy value. So you can provide both at the same time, more or less. So there's some stacking that's available there. The other thing that this analysis that we did not include is diminishing returns at higher penetrations. You can see over here that as peaks get shaved deeper and deeper, the duration that a resource needs to last in order to really keep pushing that peak down gets longer and longer and longer. So we didn't look at some of the impacts of diminishing returns as the deployment rises. For the case of Silicon Valley load, we would need kind of 2 to 3 hours of duration if we kind of stick in sort of 30 megawatts or less. As we get more and more megawatts, that duration gets longer and longer and longer. Most of the resources we looked at do have available durations over 3 hours. So we wouldn't expect very many diminishing returns, at least in the range that we were looking at. But as the deployment could grow larger, that becomes more significant. So I'd like to hand it back over to Amy, who's going to talk about what Silicon Valley Clean Energy has done with the results that we gave them.
Yeah, thanks, Brent. The results that Brent shared have been very critical for guiding SVCE's VPP activities. And of the key takeaways that Brent mentioned, which are kind of reiterated here on this slide, we're basically following all of them. So it's a little bit boring in that respect. We are focusing on specifically the load shaping approach as opposed to the market integrated approach. We have 2 initial pilots that are not only focused on load shaping, but target specifically capacity and real-time value streams. There is an additional emphasis on the resilience value for the customer, especially for one of those pilots, given the resilience issues that we've been facing in California with the grid shutoffs. As far as assets, though, we have been focused on EV charging in particular, and also behind-the-meter storage, again, because of the customer resilience value. And then regarding the last takeaway, one of the 2 initial VPP pilots specifically is a telematics smart charging pilot to really help provide the tools to EV customers that to enable them to easily respond to PUE rates. And so that's what we've been up to. We have several, again, key pilots underway. We continue to leverage these results and work with Brent and Send to develop a broader VPP program in the coming year. And thanks to Brent and Send for all of your work on this analysis.
So that's all we have. I'm happy to take questions during the Q&A. Thanks.
Thanks, Amy and Brent. And now our final speaker for this session. We're going to hear from Rahul Kar, General Manager, New Energy for AutoGrid Systems. Take it away, Rahul.
Thank you very much, Daryl, and welcome everybody. So in the next 10 to 15 minutes, what I'm going to do is give you a quick introduction about AutoGrid and also some of our thesis around VPP and share some of our software experience, how we have delivered on virtual power plants globally. Before that, a quick introduction of who AutoGrid is. So we spun out of Stanford in 2011, and since then we have been a pure play software provider working across a wide range of different kinds of companies. See, we work globally across 12 different countries, 4 different continents, and we are very proud to call some of the leading energy providers and vendors and companies as our core customers and investors. So what we have done since 2011 is we have provided flexibility management in a variety of different ways. So this may include demand response, or it might include renewables aggregation, to microgrids, to different kinds of and ways of participating in wholesale markets. So what we are selling in the marketplace essentially is a software platform, which we call Flex Platform, on which there are a variety of different use cases that our customers can run. So our customers can start with any one of these solutions. So for example, they can start with a demand response program, or they can look into EV fleet aggregation, or look into wholesale renewables participation and nomination. And the beauty of the platform is we support all these different use cases without having any one of our customers go in and buy a separate solution for each one of them. So not only does this lead to better cost optimization and efficiencies, but from an optimization and VPP perspective, we now have the capability of cross-optimizing across all these different types of aggregations that a potential customer is going to look at. So this leads to added value stacking and more IRR for every dollar you spend. So let's talk a little bit about why we are seeing an emerging growth of VPPs. And I'm sure most of the audience is no stranger to this. But with the increased decrease in the cost of storage, increased adoption on EVs, participation of renewables, and the emergence of energy as a service model, not only to the utilities, but also some of the other alternative companies. So for example, oil majors are seriously looking into the space of aggregating different kinds of assets as either mixed VPPs, and then looking to monetize that either in the market or taking that into utility run programs. For example, the RA program in California that we just heard about. So essentially, we are at an inflection point where all this starts making economic sense. And for us, we are actually seeing this trend not only in North America, where there's increased adoption of VPPs, but also globally. So for example, markets are deregulating across APAC. Sometimes there is leapfrogging where grid services becomes really important right from off the bat. So in all these different areas, and Australia included, emerging VPP plays as a business model is actually getting a very strong traction. So essentially, when we think about VPP from a software perspective, there are several functional areas that we focus on. So this starts with initial onboarding and configuration of assets and customers. We provide situational awareness and monitoring. Perhaps the most important part of this is the forecasting and optimization engine. And then finally, how are you able to make sure that you dispatch based on the commitments that you have either to a utility for grid services, or even going into a market where you're offering services from an ancillary perspective or from a capacity perspective. And finally, rounding all of these together into long-term performance tracking. So these are primarily the core functions that we see emerge from all the different VPP applications that we have rolled out worldwide. So let's get a little bit deeper into the software architecture itself. And this is where we'll spend a little bit of time understanding how a VPP construct actually makes sense from a scalable perspective across the globe. So first and foremost, like I talked about, onboarding the DER assets and controlling becomes a key essence of any VPP solution architecture. So we at AutoGrid are able to do this in a very scalable fashion because we have actually built out a universal connector framework where we have abstracted out how you connect to all these different grid edge assets. So this includes either connecting to large wind farms or even going down to a thermostat level at a residential home or an EV charger. And the way we have done that is through a variety, three different ways. One is we integrate over APIs. We prefer integrating over open protocols. And in most CNI and industrial cases, we have a universal SCADA framework by which we can both control and onboard all these different assets. Not only that, we have also seen business models emerge where third-party aggregators are themselves providing flexibility as a data stream and control directly into our platform. So in this case, they are the ones who are abstracting out all the assets underneath that. So our platform currently enables that as well. So once we have all these assets and aggregators onboarded, this is where our planning and optimization really comes into play. So we do planning and optimizations in a variety of different stages. So the one I'm going to focus on here is the portfolio coordination. So definitely as mixed asset VPPs become more commonplace, especially with the FERC rulings and with the deregulation of markets elsewhere, one of the things that is emerging as a key requirement is the ability to actually dispatch from something that we call a pool of pools. So in this case, you might have an EV program or a thermostat program or a DR program or large-scale renewables. All of these could be aggregated together, and then with economic optimization based on market constructs or constraints, you can dispatch across all these in the most economical fashion. So that's what our platform does as well. And alongside that, we obviously do our own forecasting, bring in like a lot of different proprietary forecasts, and if required, optimization layers as well to interface directly in a utility construct. And then finally, we abstract all of these out together from a system operation perspective and offer the flexibility that we gather from this operation either directly into a market. This could be a variety of different market products based on which market allows you to value stack and then which market doesn't, or go directly into even utility run programs where you offer grid services. So this is essentially what we are doing across most of our customer bases. So for example, we are rolling out one of the largest VPP aggregation with our work with our customers and partners in the US, where we are doing residential solar plus storage aggregation. We are using the same construct from a grid-connected microgrid perspective across the APAC region. The same construct then applies to large-scale renewable trading as well. Essentially, this is kind of the scalable solution architecture, which is emerging from a software perspective. So why is this problem hard and why is this problem worth solving? So let me spend a little bit of time setting the problem up. So effectively, if you think of even a single site where you have, say, solar plus storage, and they are sitting behind the meter, there's a variety of different metadata and constructs, including constraints, that you have to take care of. So for example, what tariffs is this customer on? What are the market prices? What is the specific nature of the DERs that you're trying to optimize? What is the battery chemistry, for example? What is the life cycle efficiencies? Can you actually forecast the load down to the LMP levels? Is there price forecasting required? So even for a single site, for grid participation or market participation, this is a complex optimization problem. So for example, in this instance, we show you the number of variables or the number of constraints that we have to take care of to even optimize a single site. But now imagine scaling this up to tens of thousands of different sites. So this is where the problem becomes really, really difficult. So not only does your constraints blow up, but also you have now to take care of all the different market rules, etc., which makes this an NP hard problem to solve from an optimization constraint. So effectively, if you use traditional methods for optimizing a VPP, your problem is going to blow up, the computational costs are going to blow up, and in most cases, software platforms are not able to scale accordingly. So because of that, we have spent a significant amount of time developing IP around how to meet this exponential cost curve and linearize that by using advanced optimization techniques, by decomposition techniques, and also use some homegrown solutions by which we decompose and the problem and use software techniques where you do not have any kind of choking points. So that has actually led us to deliver on scalable VPPs, meaning we can actually optimize tens of thousands, even hundreds of thousands of sites, which require this kind of optimization. So that essentially is where we have a lot of IP built in within AutoGrid's construct, and we're seeing a lot of traction in the marketplace. So how do we then take all of these into account and what is basically happening in our platform? So I wanted to spend a little bit of time explaining the construct of optimization for a VPP, because this essentially allows us to deliver on both grid services contracts as well as market optimization. So effectively, there are three main blocks into our platform that delivers on a VPP. The first is the forecast engine. So this is where we take in historical data, even metadata of all the different DERs that we optimize, and then we run machine learning to able to predict in the future how your site load is going to behave, how the baseline is going to change, how your net load is going to change, as well as generation forecasts. That feeds into our planning optimizer. I touched upon this, but this is the actual computational heavy planner that figures out in an economic sense what is the best way of operating this VPP to give you the maximum amount of value stacking. It takes into account all the tariffs, the market rules, the specific forecasts around prices, etc., and then injects the most optimal plans down to a dispatch optimizer. So this dispatch optimizer, by the way, is a very fast running control group. While this runs, say, at 15-minute or 1-hour intervals, this takes into account real-time data coming back from some of the smart loads. And if there are any malfunctions or if there are any variances to the plans, it makes very quick action. So this is what essentially, if you have grid services contracts, make sure that you're delivering on that. So this, by the way, is what we call our predictive controls technology, and essentially drives our VPP construct in the backend. Excellent. So in the next few slides, I wanted to show you a few examples of our deployments in a variety of different use cases. So on the left-hand side, you would see where we are monitoring different kinds of assets, DER assets. So this is large wind farms, solar farms. We're also doing portfolio monitoring. We have real-time monitoring and in this case, tracking. In case there are assets which go offline, we are also able to quickly dispatch and alert system operators. So we do all kinds of forecasts. So this is generation forecasts. We do both site load forecasts as well as look ahead and see how your baselines are going to change on DER operations. We then overlay actual net loads coming back from the sites itself on that. We also do system level forecasts where, for example, we are looking at if you have any kind of coincident peaks, how do you act? What are the likelihood of the next day being a coincident peak, and dispatching based on that. So all of this actually feeds into our downstream optimizer, which then extracts the best way of not only operating each site behind the meter or front of the meter, but also on a portfolio basis, extracts out what is the flexibility available both up and down. So on the left-hand side, this shows you at the single site level where we are doing demand charge management, also delivering on TOU, also forecasting what the site gross load is going to look like. And on the right-hand side, the graph shows you where we are actually doing this for a portfolio of different electric vehicle fleets, where we are extracting the up flexibility as well as down flexibility, while at the same time making sure that the local bill savings for a per customer basis is met. So this is classic value stacking. And finally, this actually shows you how we are using the VPP in order to satisfy grid services contracts. So in this case, there was a test program that we ran because in most grid services contracts that you have to actually dispatch to show that you're actually meeting the constraints and meeting your commitments. So in this case, we are monitoring the pool level or the portfolio level baseline, the portfolio level net load, and basically the difference between these two is your pool flex delivered. So when there was actually a demand response or a capacity call from the market, we were able to deliver and redispatch across, I think this was roughly about 30 different sites very early on to show how you actually deliver on that grid services contracts. So this is how we are actually using VPPs to provide not only grid services, but also operate across different market constructs globally. And I'm happy to take further questions going forward. And I do also have my contact information on the slides. So in case if you're interested in exploring a little bit more, we do have a few white papers on our website, so feel free to explore. But we're actually seeing a lot of traction globally. Happy to chat about that at a later time. So thank you very much. Happy to take questions.
Thanks for that, Rahul. And I'm going to come right back to you, because what you said at the end there, where you said, proving that you're meeting the terms of your contract. So if we have those contracts, who's writing those contracts? Who are, I guess you're I don't know if you're the customer for those contracts or just the facilitator, but how does that process work?
Yeah, that actually leads to a variety of different business cases and business models that we have seen. So for typical project developers, for example, someone who owns large assets or someone who actually is looking to aggregate assets from a VPP, they would be the ones who are actually going into the marketplace and signing those contracts, or going to a utility and signing off on those contracts. And then they use our platform to make sure that they deliver on those contracts. In certain cases, utilities themselves are the aggregators. So in those cases, they are the ones who are going into the market where they have wholesale market exposure and using our platform to deliver on those contracts. So it can actually go both ways. And in between, there are also different business models that are emerging.
Well, I think the one takeaway that I had from everyone's presentation was that there appears to be a lot of business opportunities for utilities and others in terms of VPPs. Alexandra, I want to come to you. You had the case study and talked about the brewery, or as you mentioned, the malt house. And I'm curious, is there a business opportunity for, say, a commercial and industrial enterprise in terms of setting up a VPP, and how could a C&I enterprise benefit from doing that?
So at the beginning, a very important disclaimer. In Europe, demand response is generally not so popular as in the US. And in case of European countries playing with the load shifting or with price arbitrage of the consumption units, it's rarely profitable. When it is profitable, it's with really big consumption units, say that have at least 5,000 hours of operation in a year, minimum of 1 megawatt of really flex part. In each of these hours of the year. So that is the moment when we can start thinking about really benefiting from demand response programs in terms of shifting the electricity consumption. Here, my example was with the brewery or the malt house. There was a gas consumer. So it was a very big off-taker in our power to gas, power to hydrogen project. In fact, our focus was more on optimizing the performance of the electrolyzer and using up the surplus of green electricity that otherwise would have to be curtailed, or otherwise would have to be sold on the wholesale market for a negative price. In fact, sometimes in Germany we experience this a lot. And now we could use this electricity not to curtail it, not to sell it for a negative price. We could use it to create a value, right? To create a green hydrogen that could be used by other consumers who would anyway burn something, right? And now they are burning methane plus a bit of green hydrogen.
Okay, excellent. Thanks for that. John, I want to come to you. I know the answer to this, obviously. Are there business opportunities for ancillary services? I think that's a definitive yes, but how can utilities prepare for coordination with markets? You talked about the data requirements and everything else. You know, how would you convince a utility or persuade a utility to participate in this? I tend to look at it and say, well, maybe they'd say, boy, there's just so much that we have to wrap our heads around here. What's the best way to go about talking to a utility and about how to participate in this market?
Sure. So I would first want to know where they're located, because certainly, you know, what markets are available to them, how progressive are those markets, are they regulated, unregulated, you know, some of the parameters that we've all talked about on this panel. But I would say the good thing is technology is certainly available, that we're seeing a tremendous amount of pilots and proof of value of the various utilities. I don't think it's controversial to say that regulation is certainly lagging, especially in the US, but hopefully things like orders like FERC 841 and 222 are going to really open up that door so that we can see more of this use of aggregated DERs. I would say other areas like Australia, we're involved in a microgrid project, part of a large Australian campus, that they already are aggregating all their flexible load of all the different buildings through building management systems. They're leveraging EV charging infrastructure as well as battery storage and PV, and they are bidding into the ancillary markets or soon planning to be able to bid into those ancillary markets in Australia. So I do think that there's going to be a tremendous amount of opportunities coming that utilities can be taken advantage of. And I think that they should start doing their homework now and start looking at what technology providers and solutions are out there to be able to enter some of these opportunities in the very near future.
Thanks for that, John. Amy, I'm going to come to you. We have an audience question. What are some present technical limitations, hardware, software, communications, et cetera, that are limiting VPP capabilities?
Yeah, that's a great question. I'm not sure if I'm in the best position to answer it, since at least for SVCE, given we launched in 2017, we're really in our early stages. So we have 2 VPP pilots that are launching effectively right now. So a lot of the, some of the kind of technical aspects and limitations we may not have actually discovered yet. And so there may be other folks on the call that, including Brent, that may want to comment on that. It's a pretty broad landscape, I would say. So yeah, I'll leave it to others.
Yeah, Brent, you want to weigh in on that?
I mean, I'll say that I know that there are a lot of people in this space, and everybody's kind of thinking about how do you do it. You know, I can think of the company that used to be Tendril is now called Uplight. You know, a big part of their platform was controlling smart thermostats, but creating a platform that can then control other things through similar infrastructure. And I get excited thinking about the opportunity for distributed load control, load flexibility. When you think about, you know, how many houses have and businesses have communications infrastructure already because we've got wireless internet. You know, you have everybody's got a phone in their pocket or a computer or desktop at workstation, you know, so you've got user interface devices that can, you know, talk through a cloud. There's a lot of opportunity, and I think a lot of the problems that used to be in place for demand response, you know, being one sort of old school example of VPPs, you know, you used to broadcast an FM signal or something, right? We have a whole new infrastructure now that creates a lot of opportunity, but we're still early days. And so, you know, the aggregation problem, Rahul was talking about the control problem and sort of the predictive control element of how do you optimize among all these different assets. So a lot of that stuff's tricky, and there's a lot of people who are making progress in those spaces. But I think, you know, having the infrastructure in place now that we have creates a lot of opportunity that didn't used to be there.
Yeah, thanks for that, Rahul. I'm going to come back to you. You made the point about cross optimization and value stacking. If you're talking to, say, a utility or even a commercial and industrial enterprise, how do you really, you know, sit down with them and walk them through everything that you discussed with us here today?
Yeah, so that's an interesting question, because oftentimes we want to offer this as a service to the utilities, effectively run something that we call value engineering. But typically, because we're in the software business, this is actually the front end of our sort of sales process, where we actually would sit with a utility, think about their strategy, looking in the market construct that they're working on, look at what opportunities there are in terms of value stacking. Definitely, we are not in the same class of like what Brent has been doing in terms of looking into the analysis itself, but at least we have a rough estimate of what those values are. Utilities oftentimes would be working with a similar organization as Brent's in terms of figuring out what are those different value drivers available. What we do is come in with our software packages and make sure that we are able to deliver on those. In certain cases, they may not be possible to do. For example, multiple market participation is prevented by regulation, not because of by need, because of this is based on, say, 20-year-old understanding how DERs operate, so that you can't participate in ancillary services while in real-time markets. And those things are changing. So oftentimes that clarity is driven by during our upfront engagement. And the other thing that we also see, and it's very interesting, is sometimes the silos which utilities operate in. Essentially, we have we have been able to bring different parties together in the same room, where this is the first time that they meet together and start talking about VPPs, or, oh yeah, we have been doing a pilot for the last 5 years, we didn't know about that. So basically, having them even chat and cross-pollinate leads to a lot of conversations on the utility side.
Thanks for that. Alexander, I want to come back to you because I know that you support partners in realizing VPP and business models. So are people coming to you for this, or are you reaching out to people? How does that work for NextKafka?
Of course, it's both. But I would say that we obtain, well, every day several inquiries about supporting someone in setting up a virtual power plant. And of course, the use cases and the scale of the businesses differ. Sometimes it's a startup who would like to and try out first use cases with several batteries, say to deliver ancillary services, or with electric vehicles, which is actually already allowed in Europe, in the Netherlands and Sweden. We are seeing many countries rolling out this opportunity for not only for pilots but for commercials. And sometimes it's bigger utilities who come up with a figured out business case and just need a technology to support them. So as I mentioned, it's everyone that reaches out to us.
Thank you, John. I'll come to you. I know distribution modernization, and how would you look at VPPs as an answer or a solution for modernizing power distribution?
Well, I mean, very much like we said, or like I had mentioned in the presentation, that coordination opens up a lot of new use cases. One certainly is like a targeted demand response or targeted approach to the distribution, because as we think of VPPs and interactions with distribution now, it's usually kind of a system-wide. That locational awareness is typically not there. Whereas, you know, as we modernize and we get that situational awareness coupled with locational awareness, we can really target parts of the distribution system that are seeing constraints or experiencing some sort of grid event. So really, I mean, we're seeing a convergence of so many different technologies that, you know, we could kind of play out use cases for days, but definitely there will be there'll be the need for all this coordination to meet all these different objectives.
Thanks for that, Brent. I'll come to you. We had the question come in about edge devices being security risks. Can the communications that you talked about really be secured?
So that's a good question. When I was at Department of Energy from 2014 to 2016, there was a big thrust that was starting to move towards load flexibility and, you know, controllable HVAC, for example, and at the same time, in parallel, there was a big thrust about cybersecurity, because, you know, what are the security implications of somebody hacking a ventilation system in a hospital or something like that? So I think that's a very important question, and I think it's a huge issue. I don't know that it's necessarily an unsolvable one, though. So, you know, I think it's important, but I think we can figure that out. We can figure out how to secure resources better and have more secure communications and more secure authentication systems. Like that's a problem that's been solved elsewhere. I think it can be ported into this space. It's important that it needs to be ported in, and it hasn't been yet, and that's already a significant challenge. But there's nothing about that to me that says this is unsolvable. And since we're still in early days, you know, it's just a matter of you know, navigating the challenges as they come up and working through them.
Thanks for that. Oh, go ahead.
Sorry, I just wanted to add on a few things to what Brent mentioned. In fact, last year, we actually were one of the first ones to get NERC tested with our software platform on the AWS Gulf Cloud. So because VPPs are almost equivalent to a power plant, they will be considered as critical infrastructure. So effectively, we had to go through the entire NERC process and show that we are able to withstand any kind of cyber attacks. So as Brent mentioned, this is not an unsolved problem. So it's just a matter of adoption. So we have been doing that for almost 4 years now in terms of preventing edge side attacks.
Thanks for that. And Alexander, I want to come back to you because you had mentioned you'd like to weigh in on that communications question as well.
Mm-hmm. Yeah, I just support Rahul. I see, I hear now what you mentioned. So as you, Brent said, of course, hacking a HVAC system is at a hospital is a very painful and very bad situation. But let's imagine someone hacks a virtual power plant that is having a 5 gigawatt of installed capacity under command, right? So what do we do now with it? And in fact, I would say that the grid codes in Europe are very strict about the way how the DER or variable renewable resources can be connected. So in fact, to say, for example, deliver ancillary services to the transmission system operators, we even have to create non-internet-based connections. So we have to connect, say, through GSM networks, create closed user groups, etc., have separate, sometimes pieces of hardware that, in fact, take the final execution of the schedule or of the signal or the command that is being sent to the technical unit. So there are solutions. Currently, they are quite they are quite expensive, I would say. But we could say that I think that the grid codes that are being put in place, they are sometimes treated by us as obstacles, but they are there for something, right? They are the transmission system operators, the RTOs, they really have to take care of what is happening in the grid, because otherwise not only one hospital will be hacked, but we'll have rolling blackouts or brownouts in the whole regions.
Thanks for that. John, I know you wanted to weigh in there as well.
Yeah, just one final thought. I'd say when we're talking about connecting with these edge devices, often that is synonymous with IoT. And a lot of times folks think IoT is inherently unsecure, but not all IoTs created equally. In fact, there's ways of making IoT can almost be more secure in the fact that you can actually encrypt and secure that data right at the source of consumption, where you really can make it far more secure than what we think. So I would just like to say that not all IoT is inherently unsecure or not secure.
So Amy, I want to come to you because I know that Silicon Valley Clean Energy is involved in electrification, and we actually had a summit yesterday as part of this conference on electrification. Can you talk a little bit about some of the things that your group is doing, and maybe align it with virtual power plants or just electrification in general?
Yeah, sure. Happy to comment on that. I think kind of going back to the overarching approach for achieving deep decarbonization that was shared earlier in the presentation, we're focused not just on our power supply, but also electrifying both buildings and transportation. And our programs portfolio is very focused specifically on EVs, as well as heat pump technology and induction cooking. So one way in which we help kind of weave in EPP considerations into our programs portfolio is that any program that we develop that will result in newly electrified loads, we have a recommendation or requirement, such as it's grid connected, basically such that it can slot into a future broader DPP program that we're currently developing. I can also say a little bit about some of the existing DPP pilots that relate to electrification. The first one does focus largely on solar plus storage. And again, that kind of goes back to the customer resilience need, given the public safety power shutoffs that have been happening here in California. But as a part of that initiative, so we signed a 10-year capacity contract with Sunrun, in this case for load modification. And as a part of that initiative, we're exploring expanding it beyond just the solar plus storage, but also to include EV chargers, HVAC electrification, heat pump water heater electrification, such that it is more of a whole home connected approach. We do have also the EV energy pilot that I mentioned that focuses on EV charging really as the anchor load for a customer. But the expectation is, that too will broaden to include other end uses. And so we have kind of two different pilots that focus on specific technologies, but the broader program will be more technology agnostic, end use agnostic, as well as ideally we'd be able to interact with multiple different types of aggregators and more comprehensive.
Thanks for that, Amy. And we have time for one more here. And Rahul, I'll come to you because you mentioned residential solar plus storage. And I'm curious, from a residential standpoint, how an individual homeowner would go about, participating in a VPP project. What would be the first step or steps that someone would need to take?
Yeah, great question. So I would say that in most cases, when we work with Sunrun or the Swell Energies of the world, for example, in California, or we are working with NRS Corporation in Japan, setting up a residential VPP, or in Australia, effectively, there is an upfront contract that the customer signs during the point of installation of solar plus storage. So within this contract, it could go in both ways. One is they might sign up and say they're going to get an upfront discount of installing the solar plus storage, or there might be a bill savings that might be applied to them during the period of the contract itself. So from a customer, it becomes relatively straightforward, where during the contracting phase itself, there is an upfront education saying, look, during the periods of say 2 to 4 p.m., there might be some days, maybe 12 days a year, that we might be actually using your storage device to provide grid services to California, specifically when there are either wildfires or there are flex alerts going out. So this is explained during the customer onboarding process and the customer acquisition process as well. For example, when we are working with Sunrun, they actually roll this out during the customer acquisition process itself.
All right, very good. Thanks for that. That's all the time we have for questions today. I want to thank our panelists, Alexandra Radwanska, John Grooters, Brent Nelson, Amy Bailey, and Rahul Kar. Great information and insight into virtual power plants. There is so much more that we could talk about, and I'm sure we'll revisit all of this at some point in the future. With that, thanks to our audience, and I'm going to throw it back to Kim.
Okay, thanks, Daryl. And again, thank you all for being with us this afternoon, and hope you enjoyed this discussion as much as I did. Definitely want to remind everybody to continue connecting. We are done for the day, so we're hoping to give you a few more hours of your time back to get some work done, but also to connect with one another and to network with one another. So we definitely want to encourage you. You don't have to leave. You can go back and watch any session you might have missed yesterday. You can watch anything you might have missed earlier this morning. And then we'll be back live at 9 a.m. Central with New York Senator Kevin Parker as our opening keynote presentation for Wednesday morning. So we'll see you then.
Thanks.